So here we are into basically module 2, but this is with modules, and then we have missions. And module 2 has mission 2, which is consists of a numerical analysis of numerical data and interpretation of numerical data. And this dovetails from our first module, where we introduced you to the varieties of data. And we started with categorical data. Now we're going to numerical data. Numerical data, they include numbers that you can count. Now, what one should be aware of is you can assign numbers to categorical variables, and you might sometimes see that in a lot of stats packages. You might see like an SPSS is a common stats package used in psychology. You might have, say, I used the example of gender yesterday, or sex, where you have male or female as a binary category. And male might be assigned 2 and female might be assigned 1. But conceptually and empirically, it's a categorical variable. Because for categories, there is no meaningful distance between those two values, those two groups. Is there, what's the difference between an apple and an orange? There's no numerical distance between those two. And that's why categorical data analysis used to be called qualitative data analysis, because there are different qualities between apples and oranges, right? You have the category of apples, the category of oranges, but those are qualities. And numerical data have some meaning to the distance. So, such as, for example, we looked at rankings this week among students. Well, a ranking has an order. 1 comes before 2, comes before 3, becomes before 4. Both in terms of data analysis, male and female, there's no order there. There's just the division. That's my little, I think what I hope to be a clear distinction there. Now, for the problem sets, we have a conceptual side and a coding side, right? We have each week, if you go to the R tutorials page, we have a review of the R code in detail that I provide before the assignment is due. So if you haven't seen that, take a look at that. We also have a conceptual review once the assignment is turned in, and that's when we have our hard deadline every 5 p.m. every Thursday. I'm hoping to increase the time there, so we can post it either that evening or after the next section. I have a conceptual review of the problem set. So that way it's a learning experience no matter what. In fact, I go into quite a bit of detail, and you can learn about strategies in the post-assignment review. After the assignment is due, I post the conceptual review. That conceptual review in the R tutorials page is essentially understanding how to answer the question, understanding what are some ways about thinking about things, why some answers are wrong, why some answers are right. Because learning involves making mistakes. We have to make mistakes. If you haven't, made a mistake, if you haven't erred, then you haven't learned. And it took me a long time, actually, as a statistician, to get comfortable with failure. That's why I think that's why the interactivity of using R, doing analyses, getting frustrated, breaking through that's extremely useful. And that's also why we have that's why taking quizzes, going through those as well, are extremely useful. So in these sections, I'm not going to focus hyper focus on the mission, because you have that. I'm actually expanding our range of possible concepts through different examples using the course readings, the required course readings. We have the open intro to stats readings, and we have the student's guide to R readings. Now, I conceptually divide these as more syntactic or programming oriented, and then more conceptual. But I think based on my previous section, it's actually better to incorporate both. And to begin, we're actually going to open up the student's guide to R. And if you haven't cracked open that PDF, please do so. I'm going to share my screen, and I'm going to open my RStudio. But I strongly encourage you to take a look at this, and I strongly encourage you to open R and play around with it. And by play around, I actually mean just see what's going on. So I'm gonna share my full screen here. Again, there's my desktop. And you should see me in the upper right-hand corner. I don't want to actually be cut out of frame. I was cut out of frame in the previous one. And you should not see anything else. You might see something called a Zoom account. We don't want that. We don't want this. You should, now what you should see is you should basically see R here, and then you should basically see my open intro to stats book, as well as some other material here. All right, and we're going to split the screen so we can actually share both. Am I muted now? I just realized I saw that. I apologize. Oh, I might have been muted for a second. Was I muted? All right. Here we are with the student's guide to R. And looking at the syllabus for this week, we have chapter 1 in open intro. We have pages 28 to 37. And then on chapter 3 for student's guide to R, we have 27 to 34. So before we do that, I want to point you to something, because it has been an issue in terms of installing RStudio. I want to take you to something that I think is important here, which is actually quite telling. Okay. Someone, Fatima, you are not able to hear. Is that correct? Can you? Are you unable to hear me? Oh, okay. Thank you. All right. Thank you. Okay, good. All right. That's the goal, to be heard. Now, when I talk about failure, I'm simply saying, I'm actually expressing to you something that I haven't been comfortable with until I ran thousands of regressions. And there is something about being comfortable with the data and then letting it speak. And it's a kind of a Zen orientation, I suppose. I don't know how else to put it. But speaking of failure or problems, I thought it telling when rereading the introduction. Well, first of all, when you read the introduction, take a look at this. This is not a sign, but if you're having difficulty with installation, still having problems using it, take a look at this. Read the introduction in the Student's Guide to R. Please. They talk about some installation of packages, and they have some other methods. But basically, they have quite a few links here that explain, that are other resources that might help you with installation. Okay. Now, and I suppose getting started with RStudio actually helps too, right? They can say you can run on Linux. You have the link here. That's basically perhaps not as useful, but they do have this connection to the RStudio server. So if you want to get connected to the cloud, which is something I posted on the website, take a look at that, and we have that link here. All right, the rest of this is somewhat of a brief introduction. I wanted to find something else here that was relevant. It must be in the Open Intro Stats book, which is, I apologize for moving so quickly, but there was a qualification here which basically said, yeah, yeah, okay, well, never mind. I'm not sure where it is, but I remember reading the fact that they had bugs. Let's see if we can find that bug. Yes, this was on page set 5. If you can look at this, I'm going to zoom in. And I think this is telling. These are people who wrote the book, and they're very competent statisticians. Caution, despite our best efforts, you will, capital letters, find bugs both in this document and in our code. Please let us know when you encounter them so we can call the exterminators. Right? So it's a little funny joke. But the point is, even with the foundational statisticians, the person who invented something called the F-test, R.A. Fisher, he's named after this, a reanalysis showed that he had some problems with his analysis, and you came to the wrong conclusion in his study because he didn't actually look at the data. He just ran the statistics without graphing it. This was William Cleveland, another statistician, who wasn't that critical. But the point is, you will find some bugs sometimes and you won't know what they are, which is why we provide the links to search for those. But I also like to know what those bugs are because they tend to sometimes change. Someone can update the code and then we'll see it. But I think this is actually quite telling. Now, this, of course, goes into programming wars. Why are we using R if it's that bad, if there are bugs? Well, because there are also bugs in proprietary software, too. Nothing's perfect. These are tools. Science is a human endeavor. Statistics is a human endeavor. And if you're getting a data science certificate, there'll be more emphasis on that, a pretty hard line between statistical modeling, which is more of a human-centered endeavor, and then machine learning, where you're actually you're letting machines do the work here. Otherwise known as unsupervised learning. Well, the reason we still have statistics in the data science curriculum is because statistics is based on inference and probability. It's about statements, probabilistic statements based on what is outside of the realm of our particular data set. And that's the second half of the course. But probability is crucial for even in machine learning, because machines actually use probability. They take what we know and then we make our best guess about what's going to happen with other data sets, with the future, what is actually going on. Okay. That was a bit of a disquisition, but the point here is I encourage you to, in addition to read the assignment, reread that introduction and engage interactively with the assignments. Okay, we have a question here. Okay, someone is unable to hear. All right, thank you. Let's see if we can. Andre, can you hear me at all? No. Andre, can you hear me now? With someone who cannot hear himself. If you can, make sure that your audio setting is available. You can actually deactivate your own audio, or maybe on your machine, as is typically the case. Let me take a look. I'm going to look at the attendees here and see what's going on. So I apologize for those of you who can hear, but I just want to make sure everyone's included in this. Shoot. I don't want to hide the video panel. Let's see, let's go to the audio settings. So my audio settings are all right. Now I want to see if there's, for those of you who maybe can't hear. Well, I apologize. I'm not sure what's going on here, but if you can, Andre, I apologize. But I can encourage you, I do reassure you that we will post this to the websites immediately. So totally fine if you want to head out, and I'm sorry, but you are able to see what's going on. I'm not sure why that's an issue. That's never been a case before. Okay. All right. So let me get us back to square one. We're going to go to the Student's Guide to R. Sorry, to the readings here. And here we have open on my Mac computer two sections. The first one, the one that we're focused on this week, we're going to continue with this introduction to data. And this is examining numerical data. And I actually don't want to go to that. I actually want to go to this right here. Because I want to work interactively on this. I apologize. I'm going to decrease this. View, we're going to look at this table of contents. So before we did one categorical variable, now we're looking at one quantitative variable. Notice if you look at this section, we have numerical summaries. And yesterday or the previous time, we talked about measures of central tendency and of spread. And now I'm going to talk about graphical summaries. And we did that at the end. We talked about histograms. So let's take a look at these numerical summaries. We went all the way to everything except the quantile. Now, the reason if you haven't attended the previous section, the reason I encourage you to use the Student's Guide to R is that you can work very interactively just by highlighting in your PDF or in your reader the code and letting it use the available data set that they have provided, which is a randomized control trial. That's what an RCT is, which is an experimental study of an intervention helping, I believe it's homeless people. And we're looking at something called the CSD, which is a depression score. And it ranges from 0 or 1 to 50. So it's a numerical variable because you can be more or less depressed based on your level in the score, which is probably, I assume, just the number of answers that you give in a kind of a diagnostic questionnaire. We talked a little bit about some of these functions, the functions in the text are in bold, and they're not in bold within R, but you can always see what the function is, because to the left of it is that little chevron or the caret, and you see it in your console. I'm going to click to the console here, and you'll actually see the code that I posted to the R tutorials page, or sorry, to the sections page, and on the YouTube channel. And this is the code we ran before. And the nice thing about saving your code like this, I'm actually going to save it again, is that you can highlight it, you can rerun everything you've done before. So here I am clicking it, and here we have all the output, all the answers that we've provided before. I'm not going to go through this because we've done this already. Now I want to talk about something called the quantile. Now, what is exactly a quantile? Well, it's another graphical summary of numerical data. Now, a quantile, if you know what, if you can divine what that means, it simply talks about, it's a way of dividing a numerical variable into 5 different groups. And those groups are of equal size. And that's the point that I want to talk about here. So the point is, no matter what the distribution is, what a quantile does is it separates it into 5 pieces. And we know, and you might be familiar with the concept of percentile, right? So what is a percentile? If you take a standardized test and you take a percentile and you are in the 50th percentile, we'll say the 75th percentile, that means that you are by the way, I'm sorry, I said quantile, I actually meant quartiles, because you're actually splitting it up into 4 groups, right? You don't have a group of 0%. You have those who are in the bottom quarter, those in the next quarter, those in the 3rd quarter, and those in the 4th quarter. I apologize. I just misused the word because of the term quantile is the name of the function. And the reason I think the logic behind the naming of the function here is that we're actually to have four pieces, to have 4 things, to have 4 items, you actually have to cut it 5 times, assuming that we have 2 endpoints. So you have the 2 endpoints, then you have the 3 in the middle, and that gives you 4 pieces. You know, I think a good example might be if you take a piece of, I'll be a little silly here, but you know, okay, I want to make quartiles out of this little thing here. Okay, well, I'm going to cut off this end. This is my top. Here's my bottom. There's my 2nd cut. And then we have a 3rd. And then we have our 4th. And then we have our 5th. And then here we have, well, then you have 4 pieces here. The main point here is you can have quartiles, quantiles, deciles. You can have, I guess, terciles. You can have what is called a median splits, which is you take that median and you cut it into 2 pieces. The point is that those are of equal size. It has nothing to do with the numeric value. It has to do with the amount that belonging in each category. So if we take a look at this variable, and I'm just going to run it here. Obviously, you see the outputs, but I'm going to take us back into R, and we're going to talk about. I'm going to do tiles, percentiles, quartiles. I'm going to press Command S to save this file. And here we're using the with function, but we don't typically use it because they like us to use the formula function, and I like it too. It's more intuitive. But because we're using this one, which I don't think it's actually in the course material, but it is important for concepts. What we're doing here is we're dividing the sample into 5 equally numbered bits. So let's evaluate that bit. We're going to press the run here, and we have 5 pieces. So that's you know, essentially what we want to know here. If you look at this, you'll see a little bit of jargon here. A function, as I keep talking about, is often called a command in other stats packages. It's in essence, what are you going to do? And whatever is in the parentheses, a command has to have a parentheses or a function. It's mathematically, if you think about functions, you might know what a function is. You'll see something like y equals f of x. That's a function. And the way I kind of think about it, you can think about it many different ways, but it's basically a function is a tool. If you can think of it as a piece of a machinery. Maybe it's a blender or a coffee maker. Whatever you're going to put, ingredient you're going to put in X, or arguments, or bits of pieces, some mechanism will occur in the function, and out will come Y, the outputs. That's the logic of these functions. That's what a function is in our language. And it comes out of computer science and mathematics. But that's important to know when we use the word function. And you can identify these functions here, because here you have the median function. And then you have a bunch, you can ignore this gobbledygook in the middle, right? The function here is to find the median. SD, to find the standard deviation. Here it is to find the mean. That's the average. So these are measures of central tendency. And here we have quantiles, where you're just splitting something into equal numbered groups. Now, what we're going to use probably more often is the fav stats function. And this is in Mosaic proper. And I love this. I encourage you to use it. I think that's probably why they call it fav stats. It has all the bits of information that you really want when you're looking at the executive summary of a numerical variable. And let's do the fav stats, and we should be able to use that tilde function, but yeah, they do use the formula notation here. And the formula notation, of course, is you have this function here, fav stats. You have the tilde, which is sort of like an equal sign, where I wrote that little y equals f of x. This is sort of like function, but whatever that function is a consequence of the variable we choose and then the data set that we have. And notice we use equal signs within the parentheses. And there's might be a little bit of confusion for some people out there, because equal signs, they have the transitive property, right? But in R, you're always going to read it from left to right. You're going to write the code from left to right. For now, I would say, if you're new to it. You can technically do it in other ways, but we want to think of these arguments within the parentheses as written this way. And all this is saying is that we're taking this variable, and then we're defining the data set that we're going to use as help RCT. And notice that the data sets and the data set names and the variable names are case sensitive. Everything in R that's defined as in your environment is case sensitive. We often call, I think we call it camel case, camel case. Here I'm doing something, here I'm going to define an object, and you're going to see it in this upper right hand corner. And it's going to be, it's going to be, say, our fav stats stuff. and I'm actually introducing something to you that's new called the assignment operator. That's why we don't like to use equal signs too much. The assignment operator is this little caret and a hyphen. And what that does is, it's called an assignment operator because it is actually directional. It's saying this stuff to the left that the arrow points to, that the caret points to, is our object. And our object is going to be right here. And it's going to be the output from this analysis. But in fact, I'm actually going to do something a little different. I'm going to take something a little bit simpler. Notice if we look at our measure of standard deviation from yesterday, we have this little thing here. We have 12.5 and we have the number 1. Well, that's interesting. I'm actually going to copy and paste from the console, which is what you can do. We're going to do that. Now, I'm going to take that, instead of leaving that 12.5 in the console, I'm just actually going to run the code and then define it as that object. Look at this. Here we have camel case, and it's called camel case in programming languages because you can sort of see the humps of the camel, meaning that R is case sensitive. And by the way, everything that you print out can be defined as an object. And if you haven't gone through the 16 odd R tutorials, I do talk about that. But it is important here because you'll see it, especially if you go beyond and look online. And it's important to keep in mind when you look at the assignment operator, but also when you're troubleshooting, maybe you're encountering issues and you're wondering, why can't I upload the data sets? Why isn't anything working? Well, because it is case sensitive. It wants me to use that one. I pressed escape, and I'm going to try to define this as just simply the mean of that. So we're going to take that same variable, and actually we'll do the same thing. We'll define it as a standard deviation. And I'm thinking, okay, well, it's the same word, but now we just have 2 of the same thing. So we define 2 objects here. Now, one of the reasons a lot of people don't like R, especially if you're a Pythonista, which is a person, I guess they like who likes Python, is this is called a global environment, which basically means if you define an object, it ain't gonna go. So you have to put it in the garbage. And for people like me, I like to keep things pretty clean. I feel very uncomfortable if I'm running a lot of code or using someone else's code and they're just polluting the environment, figuratively, with these global objects that won't go away. Because maybe I'll do something else and I'll call something else the same name, and then all of a sudden I'm using another object here. So I only say that because when we say global object in programming languages, global simply means it's going to stick around. So that's why we want to take our little broom here and clear objects from the workspace. It'll ask, do you want the hidden objects? Sure, why not? I do that every time I finish I would do that every time I finish a problem set or a homework assignment or a mission. I also, if you notice, I also did it when reopening RStudio. I saved the code that I used from last time, but I cleared my my working environments. You notice I did not clear my history, but let's do that too. Okay, so it saves your history. The history is not as important, but there is an issue there. So we learned about the importance of keeping cases. We learned about the assignment operator. We got more familiarized with the tilde function, and now we're finally going to get to the material, and I'm going to press Control L to clear my console. Remember, the console is where you're typing things. It's your text editor. In fact, if you're a big programmer and you're a coder, you can use your own text editor, and then you can copy and paste that code here. So for example, here we have this. Let's pretend I used my awesome text editor, my scripting language, and then I just type this here. Voila, you don't have to use the R script available in the script available in RStudio. You can use your own fancy one. I like to keep things integrated. I like to keep track of things. So let's take a look at this. what I'm going to tell you now is crucial for the class and crucial for statistics, because while it's not a class in R, we are asking you to interpret and understand both the R outputs as well as the graphics. And when we talk about numerical data, there's often there's a term quite often known as the 5-number summary: 1, 2, 3, 4, 5, and it's these numbers right here, which is basically what we did with the quintiles, which is essentially with the quintiles function, which is basically we split the group and we split it into 4 groups, and that group is defined by hold on for a second. Yeah. Oh, this I don't like this. See, the problem is I'm going to actually do some notation here because it's a little hard for me to show you what it is that I'm referencing here. What we have here is we have, if we're going to just forget about the mean and the SD and the N and the missing. If you look at everything to the left of this, you have the max, you have the Q3, you have the median, you have Q1, you have the minimum. Well, this is actually the same as the quintiles function, which showed the 100th percentile, which is the top, right? 100% of all observations are below this. This is the maximum. So this is a great example of data analysis informing us, because I incorrectly said, I kind of guessed from a graphical summary, that the maximum value on our depression score was 50. No, it's 60. So that's our maximum score. There's nothing higher than that. That's the 100th percentile. The 0th percentile, our minimum is our minimum value. That's 1. Now, what is our 50th percentile? Any takers? Well, I'll point you right here. Here it is. It's our median, right? The median is the middle. So then that leaves us with Q1 and Q3. What does that mean? Well, Q3 is between the 50th and the max. So what's between the 50th percentile and the 100th percentile? It's a depression score of 41. So 75% of that is the 75th percentile of all depression scores. If you score a 41, you're more depressed than 75% of the sample. Now, if we go to Q1, you are equidistant. You're in the halfway point of the depression score, and you have a score of 21. So yesterday, the previous session, we were talking about mean and standard deviation, then we went to median. Now we're talking about quartiles. And if you recall, I talked about the mean or the average as the measure of central tendency, and then I described the standard deviation as the on average, how far are the observations from the center, the mean. So standard deviation is the average distance from the center. And of course, the mean is the average. Well, the median is the center observation. Well, a measure of spread that is analogous to the median are the quartiles, which is quartile 1 and quartile 3. The first quartile defines the upper limit of the bottom 25%. Then you have the second quartile, which is Q1 to Q2, and Q2 is the median. Now, you'll be quizzed on this, I'm sure, if you haven't already seen it. The second quartile is the median, which is also the 50th percentile. Maybe we want to think about dollar bills if we want to use US currency, right? You have 4 quarters equal $1. And then the third quartile is equidistant between the 50th percentile and the 100th percentile. So these are concepts. This is not math. These are concepts. Now I'm going to say something that's maybe a little bit might be a little. I understand it could be a little confusing, but I do want to say this because it's interesting. The median, as we've said, is the middle point, the midpoint in the distribution of numbers in the variable. The quartiles, the first quartile and the second quartile, these are the medians in the lower half and in the upper half, respectively. So you take the sample and split it in half. Q1 is actually the median between in the lower half of the distribution. Q3 is the median on the upper half of the distribution. It's the middle value. Now, I'm sorry, it's not the middle value. It is the middle value in terms of the number of observations. So it's not the fact that you have, say, the value, the numerical value that is between those two, between 34 and 60. It's that however many people you would line up, you would find the middle person there, who is basically the middle value between the 50th and the 60th percentile is 41. What that means then is half of the people above the median are closer to 31 to 41, and than they are from 41 to 60. So that's a larger distance there. That means there are fewer people there. Now, keep this in mind, because when we're talking about quartiles, those are measures of spread. And when we talk about medians, those are measures of spread as well. When we talk about means here, that's the measure of, medians and means are measures of central tendency. Quartiles and even the minimum and the maximum, those are measures of spread. The standard deviation is a measure of spread. The mean and the median are their own kind of genre of measures of spread, right? They're based on the overall average and then the average distance. And that's why we only have one standard deviation, because it's both above and below. It's the absolute value. Whereas opposed to quartiles, you're finding the middle observation, and then you're finding the middle, the lowest, the middle observation in the lower half, and then the middle observation in the upper half. Okay, so we're talking about, and the difference between Q3 and Q1, that's called the interquartile range, right? And I often think about the interquartile range as the median, and then you have the upper quartile and the lower quartile. That's analogous to me to, okay, you have the average, and then you have the standard deviation above and the standard deviation below. That's kind of your two ways of thinking about central tendencies and then the spread. And the key point that I said before, and I'm going to say it here again, is that when we talk about the interquartile range and the median, and compare that with the mean and the standard deviation, the median and the interquartile range is more robust to outliers. And a famous statistician named John Tukey, T-U-K-E-Y, basically developed this and called it robust statistics, because, and he's a great innovator and he's a great statistician. And it's a robust statistics because it means that if there's an extreme outlier or extreme value, the mean and the standard deviation are going to be heavily influenced by those, but the median is not. And I'm going to tell you a silly joke, a stats joke, about means and why we want to be wary of means and standard deviations only, and why we often want to compare the two. It's not going to be funny. I'm sorry. It's statistics. Or maybe it's so bad it's good. A statistician is a person who will put her hand or his hand on the stovetop, the lit stovetop, and then the other hand in a box of ice, and tell you on average the temperature is fine. That's kind of a thought experiment for the fallacy of averages. Also, there's no average person, right? There is a middle value. There is a quartile. You know that if you've ever taken a test, sometimes you'll get the percentile. It's because they lined you up and then they put you in rank order. And that's part of the reason we actually want to look at different statistics to see what's going on. Because if there's a huge discrepancy between the mean and the median, or the interquartile range and the standard deviation, then that tells us something about the spread and about potential outliers. I don't think there's anything else I want to say except that I'm not a big fan of averages, to be honest. I think it's tyrannical, and then in fact it's how do I put it? It was controversial when it first came out. I was reading an article that was published in 1908 and was talking about the controversy in German statistics about the idea of an average, because like a lot of mathematical statistical innovations, like the number zero, like set theory, like the concept of infinity, even the average was considered like kind of a barbarism, right? Especially if you believe in understanding what's going on. Anyway, FavStats gives you what is often called the 5-number summary. I think that's what's called 1, 2, 3, 4, 5. There we are. That's what those are. That's actually what Tukey's term. But we also get the mean and the standard deviation. We also get some other nice things. We get the n. N, lowercase n, is always in stats nomenclature. I'm not going to say always, actually, but almost always. It's the sample size. It's the number of observations. So you will often hear scientists say, what's your n? Now it's a small n. Capital N will refer to the population if you see it. It's often italicized. Missing here, these are the observations that perhaps on that variable did not respond. And you will see this when you look at polling data. Quite often missingness is an issue. And in later stats courses, you'll see it's actually a huge issue. Maybe we'll talk about that later, but there was like a $2 billion project to look at a longitudinal survey of children, and they found out that lower income and disadvantaged families had higher rates of missingness because they're moving around more, they had to find jobs, and they're just busy. And missingness, according to some other variable, basically just created huge problems for it, and I guess the CDC cut funding for it. It was a disaster. I'll post that to the discussion board, actually, because it's a good example of how we should look at all aspects of the data and think about it carefully. And I want to say this, I talked about failure. Just because we have problems with data doesn't mean that the data can't speak to us. And that's always the truth. Even if it's a null finding, even if there are mistakes, there's still something to be said. And I truly believe that. As I've said before, it's easy to lie with statistics, but it's easier to lie without statistics. Okay, I know that was quite long, but we're going to go to graphical summaries here. You know what it is? I think just there's so much to talk about in statistics, but graphical summaries. A histogram is not a bar chart. And I need to emphasize this. I said this before, but let's take a look at what a histogram is. A histogram is, let's run this code. If you see my plots pane, one of the funny things about RStudio is it'll make the plot whatever shape you want. Okay, so here we have our depression score, 0 to 60. These bins are arbitrary. And in fact, all it does is it shows you the relative distribution. I'm sorry, I have a radio turned on. Life intervenes. Let me turn that off. Okay, that was a bit of a poltergeist moment. I don't know what was going on there. This tells you a measure of density, right? That's what that word here means. Now, there are a couple algorithms. There are some functions here to define density. These numbers are somewhat relative. It basically means nothing to me. I don't ever really look at that, except maybe for relative density. I do want to have more bars than fewer, because this shows granularity. But it is not a bar chart. These aren't counts. These aren't anything else. What it really is it's actually an approximated curve. So assuming, I'll put it this way. The probability that if you take the total sum of the 453 observations and their values, and you plot them relative to each other, their relative or standardized frequency, not their counts, their frequency, then you get this histogram. So what it tells us then is between this and this category, whatever the heck those are, that's the highest and that's second highest. And these are proportion, but it doesn't really tell us how many are here or how many are here or what's between these two categories. And these are called bins. And this is a way you can actually lie with statistics. If you want to really misinform people, you could have fewer bins. And then that's a huge form of like data reduction. That's kind of a reason why I don't always like histograms, because the density function may differ. That's not as big of an issue, but also because you can change the number of bins here to make it look quite different. But just think of it as a probability distribution. And you'll see this when we look at the density curve. It is really just kind of a density curve. There we are. Well, I don't want that. We're going to superimpose it with a normal curve. I think you can superimpose the density. Let's see if we can get to that. Yeah, this is what I want to show you. We're going to look at the same thing, only we're going to do this thing called a density plot. It is the same thing, only it's a continuous plot. You can superimpose these, you can adorn these, but a histogram is a measure of relative density. And keep in mind that a histogram might be more useful if you have discrete integers, discrete numbers. But if it's continuous, or if you're just looking at the shape, which is what we're really looking at, I kind of like to see the density plot here. Notice, by the way, I didn't really do much work here. All I did was change the data set. We're still looking at the same variable. That's a nice thing about a lot of this code and why I like working interactively with the reading. Here we have the same data represented as a density curve. Now that looks quite different, doesn't it? It's the same thing. What you see here, this what looks like snow at the bottom, or a talus slope if you're into geography. This is the rocky junk at the bottom. That's actually supposed to be the number of observations and where they lie. But because we have so many hundreds of observations, it's not that useful. But you sort of see what we had before, only this is, I think, a little more approximated, Now here again, the density function, there are different kinds. One's, I think, a Kolmogorov density function. There are other kinds as well. They're named after the researchers. But you kind of see, what I want to show is you kind of see the top here, you see a little bit of a slope, and maybe you see a longer side on the left here. In other words, it is left skewed slightly. And we knew that from the average and the mean. And you can see it here, right? This, if you're going to go mountain climbing, if you're really brave, you can go this way. I'd rather take that sort of bumpier, slower slope right here. What you also see is that this is a unimodal distribution, which means that it has one center of distribution, but it has a little bit of a lump there. And you can sort of see that hill here because of this right here. But the point is, the lesson is there are many different ways to look at statistics, and the best way is to have different kinds of measures. But that, and again, a histogram is not a bar chart. You're going to see more bar charts than anything else. Now, they have other graphics here, but I want to show you. Should I do this? Yeah, we'll do a dot plot. Why not? This is another measure of a distribution. And again, you can overlay these, and that's more useful. But I think, and you can look at these. But a dot plot is better for smaller sample sizes, and you see this in the code for the class. But this is also developed by Tukey. And what we're doing is we're just, instead of having these observations smashed at the bottom, we're actually going to stack them up. So especially for small sample sizes, we get to we get to actually see how many fall into each category. So let's do that. Let's run the code. Here I go to run. The object was not found. I know why, because I did not define the data here. Okay. Now there may be a bug here because I know the code that we give you in class is a little different, but nope, this is good. In a smaller data set, you'll actually see more dots. Or sorry, you'll actually see the actual observations. But here you see something that is, if you look really closely, and you can zoom in, look at this. I just clicked that zoom button, by the way, to open a new window. You can actually see these observations. And I'm sure if you really counted them up, well, I don't know what happened to our thing now. Oh, here it is. Maybe you could count these up. But what's interesting is take a look at this. You are learning things even here, even with a large sample size. There are 3 who have a code of 0. So on a depression score from 0 to 60, you're saying 0 to everything? To me, this is where logic also comes into data analysis. If you've ever taken a survey, and if you haven't, you should, I recommend that every statistician experience what it's like to take a survey. Because sometimes you're busy and you're tired and there's no penalty, and frankly, you don't want to be tracked, or you don't know what's going on. Sometimes people don't know what the answers are. These people might be saying no to everything, especially if it's a written survey. Face-to-face interviews, it's less likely. When in stigmatizing information, sometimes people will misreport. There's a lot of stuff going on here. So we can't do what Cleveland called, another statistician, mechanic or robotic statistics. You actually have to think. And this is what we have in the class. You're thinking about things. You are, in a very real sense, you're kind of like a journalist or like a sleuth. You're a private investigator. You want to figure out what's going on, and you're going to use all the available data here. You want to reconstruct. You want to see what's going on, and you're not just going to take a look at a p-value or a statistical significance and then be done with it. And unfortunately, that's so much of statistics, so much of science. But it's not what I hope to be in this class. But what's cool here is, take a look. We count 3 observations reporting a 0. Maybe we want to look at those. We can use the view function to look at those observations. We could do that. But again, this looks more like a histogram, doesn't it? That's what I'd say. We can decrease, we can drop that out. I'm going to take us to this back arrow. The back arrow takes us to the previous graphics that we just made. So the most recent one is here. We're going to go back one. Here we have our density plot. Here we have our histogram. If we take a look at those, that looks quite a lot like a histogram. It's more useful for, I'd say, an N of 30. Notice I use the word N here, because then you really get to sort of see who, what, when, where, why. And then the other cool things, you can overlay them. You can change these axes here, blah, blah, blah. There's a lot of stuff you can do here, but we have, I think, one of the most useful ways of viewing a single numerical variable or numeric data, which is graphical summaries, and this favstats function right here, because they let you see what's going on with the data. So I don't think there's anything else I want to say here except that I encourage you to look at some of these other examples. If you take a look at this right here, this is a smaller n. They actually subset it to, looks like people who were homeless and who were females, so homeless females. Here you see a good example of an n here that is much smaller. This is the depression score. Yeah, and they right in the first line, they already say, tell us what I don't like about histograms. They can be sensitive to the choice of the number of bins. These bins are these blocks here, and I'm going to show that right before we go. And this is how you can lie with statistics. I think what is the word width? It's not doing the autocomplete, so let's take a look at the script that they use. Yeah, width. Okay, so I'm going to increase the width of this to say 10, and then we're going to run this. Oh, wow, that looks quite different. Here, let's really impress our boss, because our boss wants some answers. Well, what does that do? Nothing. I mean, it kind of makes it look almost bimodal. If we increase the number of bins to 2, we made it very much smaller, right? I like that. That's granularity. You get to see a little bit more. And that actually might be more informative than, say, the density curve. But it is still a choice you make. Let's take a look at a value of 1 now. Assuming these are units of 1. Well, that's a little complex. There's a lot of ink there, right? We talk about data to ink ratio. It's kind of messy. So there are aesthetic choices as well. And you don't certainly see the density curve here. So there is kind of a fine balance between data reduction, which was the original intent of descriptive statistics. There's a utility to reducing the complexity of information, especially now. We are inundated with data. We don't want to be overwhelmed by that. This is actually why I don't actually like to use the view function too much. Maybe this is me being a little being a little too sensitive to summaries, but like this, I get lost here. I don't know what's going on. But some people like it, especially if they use SPSS, which encourages you to look at your data like that, or if they use Excel. I just do want to show you, you can, remember when we looked at that dot plot, sometimes the view function is useful because you can filter. And if you apply a filter, you want to do CSD. I don't know if we can type in, we're going to reduce this to 1. Let's reduce it to a little bit higher than that. Somehow I think it just reduced it to 1 observation, because I basically clicked on CSD to order it. And let's click on this. And here we see, well, I'm not, to be honest, I'm not sure what I'm looking at now, because it looked like the CSD, you had, oh, here are the others with, well, I don't know. I'm not sure why we don't have 1 scores here. It could be, this is what I'm thinking might be happening, that these bottom values, the 3 bottom values, might be grouped into a bin here, which is, well, that would make sense though. Who knows? But there are some advantages to looking at the data, long story short, which is that you're actually seeing some of these NAs, these not availables. And that's what you'll see in RSpeak, or yeah, I think it's called not available. What is it called? Not available, I'm not sure. But the NA code in RSpeak means that it is a missing value. And that's what exists in RSpeak. So those are, you have to omit those. But you'll see with the CSD score, there are no missing values. We have all of them. Okay, so that's what it's doing. It's taking the bottom 3 values and putting them right here. So we have, and then you can look at those individually, right? You can say, okay, they're missing some questions here. So these might be lazy, not lazy, but impatient people. You can look at, they're saying 0 to other things. Okay, there's no gender thing. They're saying no to everything. Got a bunch of other questions we don't have here, but sometimes looking at these unusual observations or outliers might be useful. Sometimes not. So in general, I think the main story is looking at a variety of techniques for analysis are incredibly useful. Using data interactively is really the way to learn. You learn by doing, and that's the truth. And you get used to getting frustrated with screwing up. And I wanted to emphasize that. Am I? Okay. And the last thing I wanted to say is, when we talk about the outputs, remember you have output here and you have output here, but you can also have outputs in your environment. And I'm going to do that. Just it's going to be called outputs, and we use the assignment operator. Here I have the favstats function, and here we have the output defined as an object. Okay. In fact, if we do view, this is a little bit beyond the course, and I know if you have to go, that's all right. I'm sorry to keep you here, but this is the problem of enthusiasm. You should be able to view that, or not. I'm not sure. There are some things. The point is, when you define an object, you have one observation, which is just what's called a vector, just a line with a bunch of values here. You can do things with those. You can save them. You get more information about them. I thought you could view them. Here they are. You can save them here, and then now you can cut and paste them into your word processor or put it as a table. And I'm making this statement because around week 3 or 4, we're going to start talking about the final projects. You do not want to just copy and paste the code and all this junk. This is back of the house. If you work at a restaurant, do you want customers to see the back of the house? No. You want to communicate. And that means when you go to work, you're going to put on your nicest clothing. You're going to look nice. You're not going to show them, as a professor of mine, you're not going to show them how this sausage is made. You're going to give them the nice sausage on the platter. That's not deceptive. It's clear, and it's communication. And fortunately, in RStudio, the plots are easy to save. You can export it. You can save it as an image, as a PDF, copy it to your clipboard, and then just copy and paste it into your word processor. I'm saying this to preface the fact that last semester I saw quite a few students who thought they needed to share the code and all this kind of stuff. No, none of that. And some of the example papers that we're going to post will show that as well. Thank you very much for attending, and thank you for listening 20 minutes over. Are there any questions? I'm sorry. It looks like I did see a question here. Someone is having difficulty finding a variable in the populated kids data set. Let's address that later. It looks like it's something that is probably related to ensuring your data frame is loaded. If you look at this, the Slack group, I think someone else encountered that issue on a different data set. If it is something having to do with what the authors of Mosaics are saying is a problem with the code, that's an issue. But let me stop recording, and then we can address that. So we will often encounter those kinds of issues. I've seen that all the time. So those kind of things will happen. You see it right here. You see my red text. Anyway, I hope this was useful for learning how to evaluate code, how to augment your preparation for the exam and the midterm beyond what we give you, because there are many questions and aspects of the course readings that will definitely help you. Thank you very much.